Now let us begin with the weakly degenerate quantum systems. So we have already seen in our previous lecture that degeneracy is an important parameter, and this can be used as a very important tool to quantify the extent of quantum effects in the system. Now we already have seen how we can obtain an expression for total number of particles in the system in terms of the energy. I mean, how many particles at a particular energy value, and of course temperature, chemical potential, and all other parameters. Now if we want to express this expression in terms of fugacity, or we can also call this as degeneracy, then we have seen in our previous lecture that this fugacity is equal to, say, A is equal to e raised to the power beta into mu. I hope you remember that. Fine. So that in this expression, if you want to write things in terms of fugacity, then this will be e raised to the power e into beta into e raised to the power minus beta into mu, right? So e raised to the power beta into mu is A. So what will be e raised to the power minus beta into mu? That will be equal to 1 over A. So that's what we have written here. So now we have expressed the same expression in terms of fugacity. So now we will be working in terms of this degeneracy. So I will be using terms fugacity or degeneracy alternately. So please note that both are same. Now let us do a little change of variable in this equation, and let us replace beta into e with x. So we actually are going to solve this integral now. So if we do this substitution, then what we can say is that, okay, beta into dE is equal to dx, because beta is a fixed number. It depends only on temperature, and we are assuming that we are not dealing with the temperature or systems with varying temperature. So in that case, we can write down this beta into dE is equal to dx. So that from here, if I write down this numerator, then what we can do, we can put from here, say, E is equal to x over beta. So that e raised to the power half will be x over beta whole raised to the power half, right? So that's how this e raised to power half has transformed. Like, okay, x raised to power half into dx. Okay, x raised to power half. Let us first try to talk about this only. X raised to power half by beta raised to the power half. This will be like this. And then of course we have to go from dE to dx. So from here dE is equal to dx over beta. So this will be dx over beta. So we already have a term of beta raised to power half here, coming from e raised to power half, and then beta here. So both when multiplied together results into beta raised to power 3 by 2. So that's what we have written here. So the numerator now is nothing but x raised to the power half dx beta raised to 3 by 2 divided by beta raised to 3 by 2, which if we substitute the value of beta, which we know is nothing but 1 over kbt, so then this beta is nothing but equal, so 1 over beta raised to 3 by 2 is nothing but kbt raised to power 3 by 2, right, into x raised to power half. So this is your full numerator. So this numerator of this integral is given by this expression. So that if we substitute this new variable in this integration, then we can find out n is equal to c into v kbt raised to power 3 by 2. So this term coming from numerator part, integral as such, say 0 to infinity. So from here we can say as x goes to 0, sorry, as e goes to 0, x goes to 0. As x goes to infinity, e goes to infinity. So limits of integration won't be changing. Now this is equal to x raised to the power half dx divided by so this is x raised to the power half dx, again coming from numerator. So numerator as such 1 over a e raised to the power x plus kappa. So beta e has been replaced with x here. Right, now we do a slight rearrangement of things here. This term remains as such. So this is equal to integration over say dx from 0 to infinity. Now what we have taken is a here. So okay, what we are doing here is in this denominator let us take a as common. I mean, let us add this term, taking a as an LCM, and then what will be there in the numerator? I mean, numerator of this part, this term. So a will be common throughout. This is what we have taken here, because this divided by this divided by a is going to give a here. This is a, and then you will be having e raised to the power x here plus a into k, right? E raised to power x plus a into k. I'm sure you can solve it. It's quite simple. So this is what we have done here. I mean, 1 plus k into a into e raised to the power minus x raised to the power minus 1. Now you would say, okay, we had e raised to power x here, e raised to power x sitting here, y e raised to the power minus x now here. So for that, what we have done is we have already taken e raised to power minus x common here. I mean, in denominator itself, we took e raised to power x common. So that first term is just 1 then ultimately. And here we will be having, because here we won't be having a term of e raised to power x, so that will be giving you e raised to power minus x. So you can simplify it, it's not that difficult, I'm sure. So this is what we will be getting after rearrangement of the things. Now let us do some more let us solve this further, and if we apply binomial expansion for this term, what we can find out here is then that this n will be equal to cv kb into t raised to power 3 by 2 integral as such. So a e raised to power minus x x raised to the power half, correct? And this thing, so now it is just binomial expansion. So 1 plus x raised to the power n, you know it well. So this is 1 minus, this is power, n is a minus 1, so minus this term as such plus higher order terms, fine, into dx. Now if we further try to see this same thing, then we can find out that this summation can be written in this compact form like this. Let us try to see some quick uh, equivalence of the two. So this term is as such, this x raised to power half as such sitting here, dx variable of integral as such sitting here. Now this is summation. So now see here we have some e raised to the power minus x, and this will be appearing in all the terms, right? So what we are doing here is we are taking this inside the integration. Why we have to do this is because you have e raised to minus x, then e raised to minus x multiplied by e raised to minus x, that will be e raised to minus 2x, then e raised to minus 3x, and so on. This is how it is going to look like. So that is how exponential term is kept here, and then summation over say s going from 1 to infinity. So that when we solve this summation, we will be finding that we can recover all the terms in this expansion. So you can work it out quickly and then can find out that this indeed is equal to this thing. So minus k raised to the power s minus 1. Now see, we are still working in terms of k here, sorry, kappa you can say. So we are still working in terms of this. Now this formalism is general as of now. If we take k to be plus 1, this would refer to fermionic systems. If we take it to be minus 1, this would refer to the bosonic systems, correct? So same thing. Okay, so this is equal to minus k raised to the power s minus 1, and all these things. So you can find out a raised to power s. So first when it will be multiplied with this, it will be a. Here it is a term of a square, of course. With this will be a square, with 1 it will be a. Here it will be a cube, so you can easily get this. Fine, let's move ahead. Now if I take this further, then we can write down this CV, this is as such summation over say s going from 1 to infinity minus kappa raised to the power s minus 1. So now what we are saying is, okay, I mean we can take summation here outside the integration, because these two things can be interchanged provided we don't mess with the variable of integration. So we have to keep it inside the integral itself. That's it. So now s is something that is just index of summation, and it doesn't contain x exclusively in this. A also doesn't have x exclusively here. Similarly this, so all these factors can be taken outside the integral. So this taken out, and this as well taken out. Everything else is put in this integral. Now if you see this integral which is put here can be expressed as a gamma function, can be equated to a gamma function, and this comes out to be equal to this. You should have done gamma function in your previous classes, but okay, let me not skip it as such. Let me quickly show you the basic definition of the gamma function. So gamma function is defined like this: gamma of z is equal to integration over 0 to infinity x raised to the power z minus 1 e raised to the power minus x dx. That's the basic definition. Fine. Now how do we arrive from here to here? Okay, that's not given. Okay, fine. So now I will give you oral instructions to obtain this expression from this thing, right? So I'm sure you are having notebook with you. If you can even note it down. So here you should notice that okay, gamma of z. So for gamma function, basic definition of gamma function, the power of exponential should be simple x, no factor with it. But here you would see that in exponential we have s sitting with x, correct? That's one major difference. And obviously z is so here we have x raised to power half. So if you have to obtain x raised to power half, so what should be z here? If you have to get x raised to the power half, then we have to put z is equal to 3 by 2, because 3 by 2 minus 1 is nothing but half. So one thing is clear from here, that it has to be gamma 3 by 2. But what else, or from where this factor of s raised to the power 3 by 2 came? So for that, what we will do is we will do a change of variable here actually. Here, let us do a slight change of variable, and let us substitute sx is equal to t. So you note it down in your notebook. If you substitute sx is equal to t, then what will be s into dx? S into dx will be dt, correct? So what will this become? This will become e raised to the power minus t. And now here in terms of x, because sx is t, so what is x? X is equal to t divided by s. So x raised to the power half will be t divided by s raised to the power half. And what will be dx accordingly? Dx will be equal to dt divided by s. So when you simplify things further, you will find out that in denominator there will be a factor of s raised to the power half, and then in terms of t, this function, this integral will become this gamma z. So overall it will be gamma of 3 by 2 divided by gamma 3 by 2 divided by s raised to the power 3 by 2. So this is quite simple. So that's what we get for this integral. So now we have solved this integral exclusively. Therefore, now if we substitute the values, we can write down that n here can be written as this thing as such, gamma 3 by 2 into summation over s. Now this summation, of course, this has now turned to nothing but say a raised to the power s, which already is sitting here, divided by s raised to the power 3 by 2. Now gamma 3 by 2 has nothing, no term of s in it. It's a fixed number, right? So s is coming here, so that is why it has to be taken inside the summation. Now if we look this summation and rather write it down in its expanded form. So this is cv kbt raised to the power 3 by 2 gamma 3 by 2 as such. That's all fine. And what will be this? So if you put s is equal to 1, so this will be minus 1 raised to the power 1 minus 1 0. So minus 1 raised to the power 0 is just 1. And if you put a raised to the power 1, so this is a divided by 1 raised to the power 3 by 2, so that's just 1. So this will be a directly, fine. So similarly you will find out next term to be this, next to be this, and so on. So I'm sure you can work it out properly. So here is where we were. Okay, so that's how we can write down n. Now we know expression for energy. was given by this. Now again I'm directly importing this from my previous slide. Now if you have to write down energy, then we can work out same way as we had done for n, the number of particles. So we have to work out this integral in the same way, and finally what we will arrive at this one. So E is equal to CV this. So here we will be finding nothing but a power of 5 by 2, gamma 5 by 2, and so on. I mean, that's what you will arrive at if you have to write down the energy. Now let us try to interpret our results. Now here, if I write down A naught, let me define a term A naught, or something like A naught, to be equal to n divided by this. So now you may be confused, okay, why we need to define this? So basically the physics of this lies here. I mean, this is our expression for n, correct? So now if I take everything here to the left hand side, so what will that be? N divided by CV kBt raised to 3 by 2 gamma 3 by 2. So that's what we have defined here. Fine. And what will be left on right hand side? It will be A minus kappa A square over 2 raised by 3 by 2, and so on, right? So this right hand side is something which we can say is related to fugacity or degeneracy, correct? So on left hand side, this also has to be something related to degeneracy. So this is something like a reference actually. So this is a reference for our fugacity or degeneracy, is A naught. Now let us try to talk about this A naught somewhat more. What is its physical meaning and all. So to see a further interpretation of A naught, let us try to look at this factor in more details. So this A naught will be much less than 1 and the number density is very, very small. We can see from here. So A naught is proportional to n over v, right? N is sitting here, v is sitting here. A naught is proportional to n over v. So if n over v, the number density is very, very small, so A naught will be very, very small, obviously. Similarly, it is also inversely proportional to temperature. So if temperature is high, very high, A naught will be small, correct? So this means A naught is related to the characteristic of the medium, right? How dense is the medium? And from here, what we can say is that, okay, if A naught is very, very small, that would refer to a system which is weakly degenerate. Because in our previous slide, we had seen that what is a system, what is a degeneracy of a system? It is related to how closely the particles are placed to each other or how high is the temperature. So whenever temperature is very high or particles are very sparsely placed or they are very away from each other, or in terms of interaction we can say their kinetic energy is very high and potential energy is negligible, all those circumstances refer to poor quantum effects, or you can say the system can be um described classically. So this factor A naught can be related to our system in terms of its degeneracy, and further of course this can be related to whether we need to incorporate quantum statistics for our system or not. So this means that a rarefied medium, rarefied means n over b is very small, right, at high temperature. So if you have a rarefied medium kept at high temperature, that would refer to a weakly degenerate system. So we are talking about weakly degenerate quantum systems. So what is the definition for weakly degenerate quantum systems? Those are the systems which are rarefied, means particles are far away separated from each other. They're not as far away as in the exactly classical systems. So these systems are somewhere in between the pure classical system and strongly degenerate quantum mechanical system where quantum effects are very, very dominant. So in these systems, the quantum effects are there, but they are not very dominant or as dominant as in strongly degenerate systems. So that's something crucial we should notice here. So this is why we discuss them separately, weakly degenerate quantum systems. Fine. Well, so I hope we had used C Earlier we had defined it to be like this. So I'm directly importing again it from my previous slide. So C, suppose, is given by this. Now if I substitute the value of C, then how we can write down A naught? A naught will be equal to, so well, this is our A naught, right? Let me substitute C and then rearrange things a little. I am giving it to you again, leaving it to you that you can do it yourself. But yes, we can then obtain A naught is equal to N into H cube. You can see, of course, H cube, which is here in this. So it will actually reach here after we rearrange things. So this is why N H cube term. Volume as such V sitting here. KBT raised to the 3 by 2, KBT raised to the 3 by 2, and the 2 pi m, this comes from here actually, 2m raised to the 3 by 2, right? So, okay, anyway, I mean, overall rearrangement can yield you this expression. Main thing is, okay, that here we have used the value of gamma raised to the 3 by 2. Of course, there was a gamma sitting here, right? So we have used its value. You can go back again in some book on mathematical physics and try to find out how to obtain standard values of gamma function. So these are already very well described there. So gamma 3 by 2 is equal to under root pi by 2. So that we also have substituted here to get this simplified expression. Now, if we try to rearrange things here somewhat more, so we can write down, okay, A naught is equal to 1 over G, this 1 over G as such. Now, whole cube. So we are writing cube here. So we are trying to express this as cube of some number. And what is that number here? H cube. So because H already has power 3, so it will come as H here. Now here N doesn't have cube, V doesn't have cube. So if you are raising them to the power 3, so we have to take care of that, and then it will be nothing but V over N. So this N goes here, raised to the power 1 by 3. So that this 1 by 3 when multiplied with this results nothing but V by N, and exactly the same. Same here, it is already raised to the 3 by 2, so 3 taken out, so it is just left as this whole term raised to the power half. So that's quite simple. Now I am sure that you somewhere have done this definition for de Broglie wavelength, and if not, I give it to you as a homework, or I may even ask for an assignment that, okay, this is H. You have seen, we have already seen H. This lambda de Broglie is equal to H over mv, isn't it? H over p. Now you have to prove that this denominator is nothing but m into v, isn't it? Or it is related to momentum. So you have to try all the tricks of whatever you have done. And then this is nothing but the de Broglie wavelength. Fine. So this term H over this thing whole is nothing but the de Broglie wavelength. So I'm using it directly here. And this V over N raised to the power 1 by 3. So this is V over N is nothing but volume per molecule, isn't it? Or volume per atom, or volume per particle rather, we should say, not atom, molecule, we are not bothered. So our system is made up of certain particles, so we are saying this is volume per particle raised to the power 1 by 3. So volume is of course length cube, so volume raised to the power 1 by 3 should be some length. We are saying, say, L, and this is typically, this can be related to interparticle separation, isn't it? That, okay, this is the volume for each particle, and if it is coming from certain length, say a certain cube of length L, means one particle is placed in a cube of length L. So this is volume per particle. So what will be the interparticle separation? Typically of the order of L. That's what we have applied here. So therefore A naught can be written from this lengthy expression into a very simplified expression, and this expression is very crucial and very important to interpret further the meaning of A naught. So A naught is equal to 1 over G, exactly this, lambda de Broglie divided by L. So this is nothing but lambda de Broglie. This is L in the denominator, whole cube. Fine. Now from here, let us try to talk about the definition of what is a weakly degenerate system in terms of A naught. In terms of A naught. So basically, we will say a system is weakly degenerate if A naught for that system is very, very less in comparison to 1. Or what does it mean? That if the de Broglie wavelength is very, very small in comparison to interparticle separation. That's something very interesting. And that is where we can, this definition or this idea can be used to apply for the cases whether we need to incorporate quantum mechanics or not. So in case the de Broglie wavelength of the particles in the system is very small in comparison to the inter particle separation or the typical length scales which our particles travel, in that case we can say that our system is weakly degenerate. And if this number is close to, say, very less than 1, close to 0, then we can say that our system will be uh, reaching to its classical analog or classical counterpart, and we don't need to bother about the quantum effects. And as this number starts reaching towards 1, we may have to start incorporating the quantum statistics, and we need to look into quantum effects. As an example, let us see some of the gases at standard temperature pressure STP and try to see their values of A naught. Okay, before I move to this, I again am giving you a assignment that okay, you have to calculate A naught for a system. So what you have to do is you have to write down a computer program. Again, you can choose whatever language. I would prefer if you put it in Fortran. That okay, how we can calculate A naught for any system. So at standard temperature pressure, you know how much volume contain how many molecules. So say 1 liter of any gas contains Avogadro's number of particle at standard temperature pressure, isn't it? So you can take this number from that definition, and then you can get L from there, typical order of interparticle separation, and then you have L, and then according to what are the particles. So basically particles, their de Broglie wavelength you can calculate, and from that de Broglie wavelength, because H over mb, you can try to find out that, or even from this definition, standard temperature pressure means you have to put T there, mass of the particle, and then you have de Broglie wavelength. Fine. So once you get that, you can find out from that one this A naught, right? And this, when worked out for different noble gases here, so this is argon here. I mean, there is a typo in the book, I believe, but I have not exclusively done calculations myself. So when you write down that program, try to put data for argon and then try to obtain A naught for argon at STP. It should come out to be equal to this. If correct, do let me know. If incorrect, then we will try to find out what does this A represent here. But my common sense says it is argon. So for argon at standard temperature pressure, it is 2 into 10 to the power minus 6. So now you can see this number is very small in comparison to 1, right? So we can say this is a weakly degenerate system. Similarly, if you try to calculate A naught for neon, this also comes out to be a number which is very less, 10 to the power minus 4, of the order of 10 to the power minus 4. Again, for neon at standard temperature pressure, A naught or fugacity is close to it is close to 0 or very, very less in comparison to 1. So we weakly degenerate. If you take hydrogen gas, now for hydrogen gas, you have to take mass m as the mass of the H2 molecule, because we are talking of H2 gas. So mass of each particle of H2 gas will be equal to mass of each molecule of H2. So that's what you have to try and then find out what should be uh, A naught for H2. So see, the advantage of writing that simple computer program is that you just have to put then the value of temperature, the value of mass, and value of L, and you will get the data quickly. Otherwise, you have to do calculation for all the things again and again. So that's why I have put this as an assignment. So now this thing is giving you a fairly a good idea that okay, all these noble gases when kept at STP, standard temperature pressure, say they would be behaving like classical gases. and they can be described even within Maxwell-Boltzmann statistics. You don't need to bother much about incorporating the quantum effects. Now let us see another very interesting example of say helium gas. If you see this gas at 273 Kelvin, which is uh, close to 0 degree, isn't it? So then, and suppose that this gas is filled in some chamber with a density of say 10 to 20 molecules in 1 centimeter cube. You can estimate how it compares with the STP, but this is of course not a STP thing, because for STP I think temperature should be close to 300 Kelvin, right? Room temperature, and pressure should be 1 atmosphere. So you can try to work out those things. But if you have kept helium at this under these conditions, we can find out that L, interparticle separation, for this particular case would come out to be equal to this much. How we have to obtain this is particles per unit volume. So we can from here estimate volume per particle, and from that we can take cube root to find out L. Fine. So this is simple, and then we can find out, okay, the de Broglie wavelength for helium gas molecules when temperature is this much, you know, mass of helium atom, so you can find out de Broglie wavelength to be close to this number. Fine. Now we can see from here that, okay, if you calculate A naught for helium under these circumstances, this should turn out to be this much. But again, I recommend you to calculate this because I have not worked it out, and this book has many typos. So if this number works out well, fine. Otherwise, you should get the correct number. Now, since you are in BSc 6, so I assume you can do all these basic things yourself. So I'm not spoon feeding everything, getting this number in details and so on. Fine. Anyway, let's come to the next thing. So now A naught is again very small. So we can say helium at under these circumstances can be treated like a classical gas, and so far so good. Fine. Now let us try to talk of helium under certain different circumstances, or what are those quantum effects? If we ask this question, what do we mean by those quantum effects? So basically, those quantum effects are nothing but those are the effects which comes into picture when this number. Let us first talk in terms of maths, then I will try to present physics of it. If I multiply n into lambda dB, de Broglie wavelength, n is the number density of the particles. So if this number is comparable to 1, so please go to previous lecture, and then there we had talked about this number. So now we are trying to talk this number in more details. So when this number means number density into de Broglie wavelength is comparable to 1, what will happen, or what does physically this mean? So you have some particles, a first particle, some second particle here, it has some de Broglie wavelength, second one has some de Broglie wavelength. If these are very far away from each other, then their wave characters are not seen by each other. They will see each other as if they are particles. Go to your previous I mean classes. Let us try to recall things. When you used to we used to discuss de Broglie wavelength of a cricket ball. So this turns out to be very less because mass is very high and momentum comes out to be very large, and the de Broglie wavelength of cricket ball comes out to be very small in comparison to the distances which that cricket ball travels usually, which are of the order of meter or at least centimeters, isn't it? Meter, centimeter. So those distances are very large, and de Broglie wavelength is very small in comparison to those distances. So if you have two cricket balls placed at a distance of say 1 centimeter even, their de Broglie wavelengths are very small, so they won't be seeing each other as a quantum mechanical object because de Broglie wavelengths are negligible. When does those effects become significant? When we are dealing with microscopic particles, right? Of course. And those microscopic particles too, when placed at a distance which is comparable to their de Broglie wavelength. So that is something which is important. So what will happen in that case whenever two particles are placed so close to each other with such that their de Broglie wavelengths are comparable to their interparticle separation, then those two particles won't be seeing each other as if those are just particles, but they will also see each other like waves, and those waves will actually execute or will display the wave like properties. So they can uh, exhibit many phenomena which waves do, like interference effects of those particle waves. And those interference effects of particle waves are nothing but the quantum effects. So, and that is why these becomes very crucial under those circumstances. So when n is very large, means number of particles per unit volume is large, means you have a large density of the particles, and lambda de Broglie is also very large. So means we have so many particles packed in a small volume, and also those particles have very large wavelength. So in that case, it is highly probable that those particles will be showing the interference effects of their what you can say, the particle waves, right, or de Broglie waves. So those interference effects of the de Broglie waves leads to or are actually the cause of quantum effects observed in the system, and that it is because of those basic effects that systems deviate from their classical behavior. Because in classical physics we say something which is particle is just a particle, something which is a wave is just a wave. They don't mess up with each other, they are not they are totally different. But what happens in those quantum systems, that the particle and wave pictures merge over to each other, and that is why that merging of these two pictures leads to very interesting things which we observe. One such example is of liquid helium. So in liquid helium, let us take now this same thing which we have discussed here. Now let us discuss liquid helium for a different uh, uh, conditions. I mean, let us take that now we have this number has say 10 to the power minus 23. This number is very, very small. Now we are saying volume per particle is very less, of the order of 10 to the power minus 23. You can find out volume per particle from here when if you have to work out. So this much molecules per unit per centimeter cube. So if you invert this number, this will be nothing but volume per particle. So here the volume per particle was of the order of 10 to the minus 20. Now we have reduced it further and we have put it, or what does this mean is that we have sort of compressed liquid helium. Sorry, we have compressed the helium particles so close to each other to yield to this small volume per atom. Now if we for this find out L, this interparticle separation, then this would come out to be equal to this. Again, I recommend you cross check the numbers by doing simple calculations yourself. Now let's take this as the de Broglie wavelength. Now this is actually typical separation among the helium molecules when those are placed under these circumstances. So then de Broglie wavelength, let us say that okay, the de Broglie wavelength of these particles should be of this order. Now how we can get this de Broglie wavelength? If you go to the previous slide, and that is related to okay, let me show it so that you don't miss the whole picture. So see, this is your de Broglie wavelength, right? So de Broglie wavelength can be tuned with the help of temperature or mass. Mass is fixed, so we can't play with this. Of course, if you're dealing with different gases, then mass can be used as a tuning parameter for de Broglie wavelength. But yeah, main thing is temperature. So in this case, for case of helium, means what we are trying to do is okay, we fixed the de Broglie wavelength and we are trying to find out what is the temperature at which helium uh, uh, atoms would lead to that de Broglie wavelength. So if we work out those things, those numbers a little, we will find out that okay, for helium atoms to have this de Broglie wavelength, which is comparable to say interparticle separation, we should place helium at a temperature of say 10 Kelvin. Fine. This means that helium, this refers to liquid helium actually. Helium or liquid helium around the temperatures of say 10 Kelvin or below this would be manifesting quantum effects, right? Because in that case, interparticle separation and de Broglie wavelength of the particles become comparable. And interestingly, it has been found that liquid helium around 4.2 Kelvin. So, I mean, it is just the threshold where the quantum effect starts to come into picture. And it has been found that around 4.2 Kelvin, this liquid helium shows a very important property of superfluidity. Means it can flow without any kind of viscous forces, no resistance for the flow. That is called superfluidity, and that is a quantum effect. So this is how this simple idea of a naught, or this simple n into lambda de Broglie, can be used to actually investigate possibilities of new interesting quantum effects in our systems. So this completes our weakly degenerate quantum systems, or the conditions where we need to actually incorporate quantum effect, where we need to uh, look for quantum effects. Now, in next class, we will be talking about another example of, say, weakly degenerate systems, or rather, we would say the quantum systems, and that will be of conduction electrons in metal. And those are this example is strictly uh, referring to the Fermi Dirac statistics, because electrons are fermions, and then we will be now seeing how those quantum effects in electrons and metal uh, can be described with the formalism which we have obtained till now. So uh, I will be coming up with this next video by tomorrow, so or maybe by today evening. So please get this done timely, so that you are ready for the next video. And if you have any questions, feel free to ask. Till then, thank you. Stay safe.